Okay, this is just background stuff, shows the vehicle on the pad. This shows Bob Crippen getting ready to fly, and there's me, and you can see my big project the week before flight was getting bigger United States flags put on our pressure suits. And the reason for that was one of these bureaucrats told me that it had to be a small flag to balance the space shuttle program, and I pointed out to him that the United States was bigger than the space shuttle program.
This shows us in the van, the traditional van that had been carrying Apollo crews out, that we rode out and going into the white room of the vehicle. Everybody had to wear those little masks, theoretically for our last week there, so that we wouldn't contaminate them or something.
They found that nobody at the Cape got sick from us being around them.
This is shutting up the hatch just prior to launch, and that's John said it gets kind of lonely out there.
This is high-speed ignition of the three main engines. The vibration in the cockpit was very low at this time after the engines light off. The instruments just a little blurred, but you could read every one of them. And look at those babies come up to speed. This is from the cockpit. Shows how the vehicle moves back and forth there. And this is high-speed photography of the bolts blowing and the solid rocket motors lighting off. And all that, this water spray right there where they're trying to keep things cool and not having much luck. And this is very high-speed photography. Because when it lit off, there was a couple of thumps, and we started moving up very slowly. Look at these beautiful shocks coming out of the main engine at liftoff, and it's moving a lot faster than that. This shows how close it comes to the intertank access arm, which has always worried me some. It's really getting up and going.
John and I expected a real hard kick in the pants. There shows that what it looked like out John's window.
It's called tower clear right from the cockpit.
But it was actually a really very smooth liftoff with very little shaking associated with it. There's the roll program to head us out over the ocean.
And the vehicle is, the cockpit vibration is such that you can still read all your instruments in there, and maybe 10 cycles per second. This shows the roll program from inside the cockpit out the side window, and it's a thing of beauty. It's just as smooth as glass. There's no accelerations involved, and this shows the vehicle speed picking up. It's probably about ready to go supersonic right now, almost going straight up. And we said that's what it was going to do, but I didn't really believe it would, but it did.
We were getting a little lost on our trajectory here that we're still analyzing right now. Also, I was seeing some debris coming off from up over the nose that was coming back and hitting the windscreen and going over the top of the vehicle that we weren't sure what it is, like ice or soapy. That's the stuff on the external tank that they're still analyzing.
I believe that tail is about 750 feet long, and maybe you can see it better from here, maybe 600-700 feet long, maybe 150, 200 feet wide. It's really impressive. I'm glad we couldn't see that.
Thank goodness for no rearview mirror. The ride was very smooth throughout this. Up in the transonic phase, it shook just a little bit. They're coming through max Q.
This is a camera inside the orbiter from the ET doors and shows the external solid rocket motor separation. Isn't that a spectacular shot? And then we show it again from inside the cabin, although the light is much brighter than this.
The big flash across the windscreen.
This shows that we never saw these pictures, but here's the picture of separation outside from high-speed cameras. And isn't that terrific?
From onboard sensations, the only thing we really saw was the flash of light and our normal avionics cues that we had dumped the solids. We did not see them go away nor feel any jolts.
We're less than 1 G right after separation, transverse G's, and this baby's just chugging along, and it's just as smooth as glass, that ride is.
Here you see some particles coming by John's window, a couple of white objects. There were one that was indicative of the kind of stuff that we'd been seeing throughout the flight.
This is this is umbilical separation back in that view that we saw, and this is external tank separation, and it is a spectacular sight.
That white particles you see there are ice caused by the hydrogen freezing as it's coming out and perfectly nominal.
There's the fitting that goes up in the orbiter. There's the umbilical plate, and there's the tank. And as you can see, all this black material there, that's the way the SOFI works. It chars and turns black. So there's a high heating area in there, and it really caught it. And there's another place that's sort of discolored up here toward the nose of the tank.
There was supposed to have been a tumble valve actuate to start the vehicle tumbling, and it did not work. And from our standpoint, it gave us a much better view of the tank. You'll also see the nose discolored.
It almost looks like the nose is it's got all the sulfate gone from it, because there's a sort of metallic color there, but that might be bright sun.
Yeah, we're not sure of that, and people are analyzing that still. This is a scene of me climbing out of the seat. All of the operations associated with the suit and the seat while you're in zero G are much easier to handle than it is down here on Earth. I'm just stuffing the helmet in a little bag along with the gloves so that we can tuck them away. There's quite a few connections associated with that suit, but it's no real problem to handle it all in zero G.
In 1G, we had a lot of problem with this helmet. It was always bumping into the hand controller and firing things. There, you see it's up there out of the way. We finally got it right.
This floats nicely.
I'm not going to tell you this picture was made right after we got into orbit, because I don't think either one of us is that gutty, but we made it later on and then ran it backwards.
Actually, we did a suiting exercise while we were on orbit just to make sure that we could get the suits and get back in the seats with no problem, and that's when we filmed this. This is two TV cameras muxed together, one on the left and one on the right, shows the initial payload bay door opening. All of that went nice and smooth. You'll notice the OMS pod coming into view right here. This is the first time we saw some tiles missing off of the OMS pod.
You notice the door kind of hesitates when it opens, too. It did this in a fixture on the ground, and they told us, well, that was due to the fixture. That's the way the door really works.
The camera on the right is an aft camera looking forward. You can see the windows coming. The one on the left is a forward camera looking aft. That door operations went as smooth as it could be, which I was mighty happy, because I didn't particularly care about the thought of going outside and trying to do anything associated with them.
This is a view, a pan in the outside that shows the radiators deployed out there. That's a beautiful, beautiful shot with the television.
You can also see those radiators when you look out your forward windows, which surprises us a little bit.
This is an ops mode 8 checkout of the hand controller. You move it full throw, and then you read on the cathode ray tube, which is where I'm looking, to see if the hand controller is working properly. And this is very exciting. A little bit of this will last you about 6 months.
This shows a camera forward in the cockpit looking aft, and with John coming out of the seat. This was actually some TV stuff that we did for a status report. Pretty good indication of the kind of problems we have with some of our comm lines, which you had to work pretty hard to make sure you didn't get tied up in those things.
And we stayed tied up in them the whole flight. The government is now looking at wireless mics that I think will really improve the capability of the crew to operate. As you can see there, I'm having to hold mine next to my mouth so I can talk to people.
This is a shot down on our mid-deck storage area where we had all of our stuff stowed, and this was actually just after the press conference, or not press conference, after the conversation we had with the Vice President. Zero G is something else. That is something that all of you should have an opportunity to experience. It is really fun.
You know, if you could do that in your living room without breaking your leg, you sure would.
There's no problem trying to restrain yourself anywhere down there. I'm in the process here of changing out one of our LIO canisters, which is used that we run the air through to take out all the CO2 and any contamination. It's a very easy job. We had a couple of troughs down there where we stow LIO canisters, and you could just fit your legs down in there and kind of push them apart, and it restrains you very nicely.
Look at this. It shows the mobility that we have down the mid-deck. People thought we needed restraint systems to tie ourselves down in there. You don't need any of that. Now watch this mobility that Bob has when he kicks off and goes up to the top side. Boy, I'll tell you, if that isn't the neatest thing in the world.
The thing about it is you don't really go flying around. You need to move a little bit slowly, otherwise you'll end up banging into something, but there's no problem controlling yourself any place you want to go.
Try that in one gravity and see where it gets you.
You see, I just was wearing my socks there. I never put any shoes on while you're on orbit. I don't like to when I'm in the house either, so.
This shows what the television will show you out the window, and shows what a great view those spectacular windows gave us. Here's another television view of the Earth.
Now we're coming up to the reason I was glad I was flying with a guy like John that's got all the experience. We're getting ready to come home, and sitting beside a man that knows space testing like he does made you feel mighty good. We're shutting the doors, and all of that again went just like we wanted it to. There were no problems at all associated with it. You can notice there's a little bit of jerky motion when it comes down. We were lowering the starboard door down easy, and you'll notice it bounces pretty good, which we're having to pass on to other following crews to make sure that when they close it, they don't have any problem with overlap. Got it all tucked away, and we're ready to come home.
Now this had them stretch this picture because in the real world there was a beautiful pink up here due to the heat. This is the first part of entry, and there's the sunrise coming up, and we're moving along at about 300,000 feet, and we're just about to 265,000 feet where we go in our first roll reversal, and you'll see that pretty shortly.
Now we're moving pretty fast, but not quite this fast.
Yeah. That's the first roll reversal. And here's the second roll reversal. It's done at Mach 18 and a half, and this is at 2 frames a second, so we're moving 6 times faster than we would in the real world. 12 times maybe, yeah. Mach 18 and a half, and you really see those clouds go by even in the real world, but it's not quite this fast.
You certainly.
The next roll reversal is at Mach 9.8. There it goes.
We did the roll reversal a little bit slower than that, too.
Yeah. And here we come back at the 4.8 roll reversal, and that's Bakersfield out there.
Coming across the Hatchby in the Sierras.
And the vehicle sort of rolls rings level, and this is about at 80,000 feet, and then we went to real-time photography, which is only twice as fast as happens in the real world, and as you can see, everything is slowed down quite a bit. We're pretty high right now, maybe 75, 80,000 feet, coming across the lake bed areas that we told you all about. There's China Lake up in that area, up in there, and you can see it out the left window.
There's Cuddyback, that Pork Chop Lake coming into view at the top.
Right at the top. We're coming out to swing around the heading alignment circle, and it sure is a beautiful view. Looking out that window, you can see everything you need to see. There was just no doubt in our minds that we knew exactly where we were in the flight, even by comparing what we had on our normal ground track with what we're seeing on the instrument. There are 3 sisters up there.
The ride in up to this point had been nice and smooth, and the vehicle controls really tight. It's a nice handling space.
Chase plane joint up there.
And we're getting ready to go in the turn around what we call our heading alignment circle. That's the Mojave River, which is mainly a dry lake bed or dry river bed out there. John is driving the vehicle at this point in time, and it's really handled nice. We were right down the middle of the corridor all the way.
Remarkable thing about the space shuttle is it's all electric, and when you move the wings somewhere, they stay there. You put the nose somewhere, and it stays there. It's just an admirable handling vehicle. You couldn't ask for anything as responsive, and as for this kind of a job, it does it exactly like you want it to.
Couldn't have ordered a better day for coming back in. We could have navigated visually all the way from when we hit the coast, which was just a little less than Mach 7 up south of the San Francisco area, all the way down to the San Joaquin Valley to the Edwards. There was no problem knowing where you were at any time.
There's the highway north of Edwards there, and you swing across the lake bed, and it's kind of hard to see at first in these films, but there's the old aim point right there. We're starting to come down the glide slope there. The runway's still hard to see there.
We have some aim lights that give you an indication of what your glide slope is out there that we refer to as PAPI lights. We also had locked onto a microwave landing system, and all of those ended up agreeing right on as to where we were, no doubt whatsoever.
Here's our old chase plane. He's flying back and forth across the bottom of the vehicle, taking pictures to see if there's any tile damage that would not show up. You know, they thought they might get some from the rocks and everything on the desert floor, so he's covering that right now. And chase plane did a real terrific job. The vehicle is very easy to control in this flight regime. We're about in the pre-flare right now.
And I was flying about 285 knots at this point. We're like about a 20-degree glide slope. Everything was just as smooth as could be.
There's, we're going into pre-flare, and this is how it looks out the window. You may be able to see 2 or 3 of those lights. 2 white lights is what we're looking for. There are 2 there. We start our pull-up now, and there'll be 3. You'll see the 3rd one come on. So we're on a 20-degree glide slope to pre-flare, which means we can only land right down here at the touchdown point. Here's the wheels coming down.
The wheels really snap down fast. They're much faster than what I anticipated them.
And there's a couple of big black marks you'll see coming up here pretty soon. There they are. That's the touchdown point, and here we go, boy. What a machine. It didn't know about that. It's supposed to land on the touchdown point.
But actually, you should understand, John was not trying to touch down on the touchdown point. What we were trying to do was to find out what the real deceleration and touch down about on an airspeed, which was about 185 knots. And all of the ALT flights and this one ended up landing long, which looks to us like we have a little bit more lift capability than what had been predicted.
And we rolled right up here so Kennedy Space Center's recovery team could get a hold of us and hook the coolant up as fast as possible. We rolled into the runway intersection. We did that on purpose, so we hardly used any brakes on this rollout, and there's the vehicle sitting, and she is a beauty. That's, believe it or not, the weight of that vehicle right there is about right around 99 tons. I keep reading where it's 150,000 pounds or 80 tons, but that one right there is 99 tons. It's quite a performance thing to return from orbit with 99-ton spacecraft and get her back all in one piece, I think.
Sunday, April 12, 1981, Kennedy Space Center, Florida. The Space Shuttle, 14 stories high, 2,000 tons, poised on the pad for its maiden flight. This is Columbia, the spaceship that will orbit the Earth. Its external tank, it holds over 500,000 gallons of fuel for Columbia's 3 main engines. And the solid rocket boosters, the largest ever used on any launch vehicle and the first to be employed in a U.S. manned flight. At liftoff, the solid rocket boosters, together with the 3 main engines, will unleash more than 6.5 million pounds of thrust needed to launch the world's first reusable spacecraft. Never before has a winged vehicle been launched like a rocket, orbited the Earth, returned through frictional heating in excess of 2,500 degrees, and landed, still aerodynamically sound, to be launched again and again. If it succeeds, the space shuttle will truly be a remarkable flying machine. There are many other goals to be reached during the 54.5-hour mission that lies ahead. 144 test objectives are planned for the flight. These objectives could not be achieved without an astronaut crew. The commander, John Young. The pilot, Robert Crippen. Young has already been in space 4 times for a total of 533 hours. He is the most experienced astronaut flying today. Although Crippen has over 4,000 hours of jet aircraft flying time, this will be his first time in space. The astronauts make their way across the access arm toward the shuttle in the pre-dawn hours before launch. An American spaceship has never carried a human crew on its maiden voyage. At the Launch Control Center, 3 miles from the pad, final steps are being completed in the countdown. Final preparations are also being made in the Mission Control Center in Houston, where control of the flight will switch once the shuttle clears the tower.
Okay, now your vent switch to open until
There has not been a manned launch from Kennedy Space Center since the Apollo-Soyuz test project in July of 1975. With this launch, Young and Crippen, launch controllers at the Cape, and flight controllers in Houston will experience the most dynamic, fast-paced series of launch events ever undertaken in the space program, all in less than 9 minutes. The most challenging ascent profile ever to be flown by a space vehicle. Photographers, film and television crews, plus newspaper and magazine writers from around the world, nearly 2,700 of them are here to cover the launch. In addition, approximately 600,000 spectators line the coastal area near the Kennedy Space Center. Arriving by every mode of transportation, they have come from every state in the Union and many foreign countries. The promise of a rebirth in America's manned space program and the dawn of a new era in space transportation awaits.
14, 13, T-minus 10, 9, 8, 7, 6, 5, 4. We've gone for main engine start.
The roll will put the shuttle on its precise heading toward an imaginary target in space.
Roll program complete.
Roger, roll complete.
Booster, go. GNC, go. Eagle, go. Go at 40, Capcom.
Columbia, Houston, you're go at 40.
The shuttle is now 40 seconds into flight.
Roger, Columbia, on the nice ride. You're lofting a little bit. You'll probably be slightly high at staging.
Negative seats.
Columbia, you're negative seats.
Should anything go wrong, the shuttle is now too high for the astronauts to use their ejection seats.
Columbia, you're go for SRB SEP.
We see SRB SEP flight.
Roger, on a SEP.
103 converge flight.
Bet.
Capcom, let's tell them all the calls are going to be a tad early because of the hot first stage.
Columbia, you're looking a little hot. All your calls will be a little early.
Okay. Yeah, map looks good here.
Stand by, press to MECO.
Columbia, stand by. Press to MECO.
Mark it.
Mark. Press for MECO.
Roger, press for MECO.
The shuttle can now continue toward MECO, main engine cutoff.
They like the VAP, Eagle, ECOM.
Let's go, flight.
Capcom, VAPs go. Stand by, negative return.
Columbia, stand by for negative return.
Mark it.
Mark. Negative return. And your VAP is good.
Outstanding. Sure is. We can confirm it. What a view.
And single engine rotor flight.
And Columbia, your single engine rota.
Columbia can land safely at the Naval Air Station in Rota, Spain, even if 2 of the 3 main engines should fail. Right now, the engines are generating over 42 million horsepower.
Miko 25, 6,
Miko.
0, up at 220.
Roger, Miko.
And
we got Miko confirmed. Miko
Roger,
confirmed, and
Columbia,
it's
Miko.
right on the money, nominal.
Main engine cutoff. Columbia is now in space, traveling over 18,000 miles per hour.
Okay, we got set.
Roger, we confirm the SEP, Columbia.
The external tank has just been jettisoned and is now falling away from the shuttle back toward Earth. The tank will break up as planned over the Indian Ocean when it comes into contact with the atmosphere. Shortly, by firing the OMS, Orbital Maneuvering System engines, Columbia will achieve orbit. Then one of the most important tests of the mission will be attempted, opening the payload bay doors. The doors must be opened before the end of the 6th orbit to expose the space radiator cooling system. If the radiators cannot be exposed, heat collected from the onboard electronics cannot be released, and the astronauts will have to return home. The OMS burns are successful. Columbia is now in orbit, circling the Earth at an altitude of approximately 150 miles. The payload bay doors will now be opened.
Okay, the port door is coming open now.
Roger, copy.
Well, you are missing one fantastic sight. Boy, that is really beautiful out there.
We appreciate those updates.
Both doors have been opened. The radiators can be deployed to begin dissipating the heat.
The doors are all opened up and hunky-dory. Glad to deploy it right on time.
And the radiators look good.
Okay, we want to show you our own pods here. We do have a few tile missing off of both of them. Off of the starboard pod, 3 tile and some smaller pieces, and off the port pod, looks like I see one full square and looks like a few little triangular shapes that are missing, and we're trying to put that on TV right now.
Roger, Crip, we can see that good.
From what we can see of both wings, tops and leading edges, though, all those are fully intact.
Within minutes, an assessment is completed on the impact these missing tiles could have on the remainder of the mission. At a news conference later in the day, Flight Director Neil Hutchison answers questions from reporters.
But you asked me if I knew where there were any other tiles that might be loose. The answer is no. And quite frankly, we're not worried about any other tiles being loose.
At this writing, is there anything at all that would lead you to say you might not go for a full duration mission?
Nothing.
Columbia, Houston, you guys did so good, we're going to let you stay up there for a couple of days. Your gopher on orbit.
Spacecraft must go for on orbit. This thing is just performing just outstanding.
Roger, we agree with that. And Columbia, Houston, just for your information, you dropped those SRBs right on target, and they were floating just the way they ought to be, and the boats were getting ready to fish them and bring them back.
Okay. The ride that they gave us was pretty neat.
The solid rocket boosters, which separated from the Columbia as planned 2 minutes 11 seconds into the flight, landed on target in the Atlantic Ocean, 151 miles downrange from the launch site. After being towed back to Kennedy Space Center, both boosters will be refurbished and used again in a future shuttle flight. The 3rd and 4th OMS burns are also successful, raising Columbia's orbit to an altitude of approximately 172 miles. For the first television transmission from inside the spacecraft, the crew will give a status report on the mission.
The flight so far has gone as vehicle has just been performing beautifully, much better than anyone ever expected to do on a first flight, and no systems are out of shape. And it's delightful up here in zero gravity, might add. Of course, we owe this to a lot of people, so we certainly want to thank everyone who has helped get this thing airborne, and can take great pride in it's doing so well right now. Okay, we're switching over to the aft camera here. I'd like to echo John's words as I usually do. I guess being the so-called rookie on this flight, I had a thrill from the moment of liftoff all the way up to what we're doing now. It's really been super. The spacecraft has worked as advertised all the way along. I think we've got something that's really going to mean something to the country and the world. This vehicle is performing like a champ, like all of us that have worked so long on them knew that you would.
Okay, sir, we appreciate those comments.
I guess that does it.
That was a good time, and I think you must have practiced. We're just about to lose your ghost song.
Just accident.
Just accident, says Robert Crippen. None of the other events of the day have been accidental. Every test, liftoff, SRB separation and recovery, ET separation and impact, 4 ohms burns, payload bay door latch opening and closing tests, radiator latch deploy and stowing tests have all been successful.
I guess we owe you guys one super attaboy for today. This is fantastic. You worked through a pretty long, hard day, and you're essentially right on schedule, which is going to be close to being a first for the spaceflight biz, I think, for first day activities. It's sure been fun working with you today, and we look forward to seeing you in the morning. I hope you get a good night's rest.
Okay, you guys did super work today. See you mañana.
Roger, thank you. See you tomorrow, guys.
Well, many hour went into this thing. A job well done by the shuttle space team. We can't say she's sleek and lean, but I'll tell you right now, she's a mean machine. The Columbia, not the kind you smoke. This here's a bird. She gets...
Morning, Columbia. Welcome to day 2.
All right. Appreciate that super wake-up music this morning. Well, we sure enjoyed it. This was a good breakfast.
Today, the astronauts will test onboard systems and also review procedures for tomorrow's landing. A test of the flight control system is conducted by John Young. The flight control system operates Columbia's aero surfaces, the elevons, body flaps, rudder, and speed brake. These surfaces are useless in the vacuum of space, but will be essential tomorrow when the shuttle lands. This will require precision maneuverability, which the aero surfaces provide. Payload bay door cycling tests help ensure that latching and closing procedures can also be done before entry tomorrow. As with every mission, many pictures of the Earth are taken by the astronauts. Over 500 on this first shuttle flight. Active volcanoes, cloud formations, alluvial fans, giant whirlpools over 15 miles in diameter, sand dunes 1,500 feet high, running unbroken for hundreds of miles. The high Himalayas, where mountain peaks reach 24,000 feet. And one of the most remarkable space photographs ever taken of the Earth, an area in Iran exposed to wind erosion, which has resulted in these breathtaking silt and sandstone formations that look more like a painting than a desert. After lunch on the second day, the astronauts receive a phone call from the Vice President of the United States, George Bush.
How's it going up there? Everything rocking along all right?
Spaceship is just performing beautifully.
Well, it's great, and everybody views it, I'm sure, just as the forerunner of great things to come. I think your trip is just going to ignite the excitement and the forward thinking from this country, so I really just wanted to call up and wish you the very best.
We certainly appreciate it, Mr. Vice President.
The crew also don and check out the ejection suits they will wear during entry. Young, Crippen, and Columbia pass every test. They are ready for the final phase of the mission, entry and landing. April 14th, 1981. NASA's Dryden Flight Research Center on the edge of Rogers Dry Lake Bed in California. A recovery convoy of 24 vehicles and more than 100 personnel are assembling here to power down Columbia after landing. Enormous crowds are also beginning to arrive. A string of traffic 6 miles long waits to enter the base. Thousands more are already here. Close to 1/2 million people will eventually be on hand to see the landing. On board, the astronauts suit up for entry. The ascent and orbital phases of the mission have gone extremely well. Now the final phase must be completed. Before that begins,
Columbia, you have a go for payload bay door closing.
the doors, which have been open a total of 47 hours during the flight, must now be closed. Then, using the RCS thrusters, Columbia will maneuver into deorbit burn attitude, head down and backwards, fire the OMS engines one last time, and descend into the Earth's atmosphere.
Nice and easy does it, John. We're all riding with you.
Columbia is out of contact during the OMS burn. Mission Control will not know if this burn was successful until they are in communication with the spacecraft over Australia. It is now over the Indian Ocean on the other side of the world, but from that distance the burn must be precise so that later Columbia will hit the lake bed target in California.
Columbia, this is Houston through Yargady. We're standing by.
Burn was on time at nominal residual 1/10.
Columbia is now committed to entry. With an RCS post-burn maneuver and several firings, it is oriented to a heads-up, nose-first attitude headed toward entry interface. This is where the atmosphere begins, at approximately 400,000 feet. From that moment until the shuttle reaches 165,000 feet, it will be in communication blackout, out of touch with mission control for almost 20 minutes. The landing site is almost 4,400 miles from entry interface. Chase planes are preparing to take off. One will call out altitudes and check Columbia for any damage just prior to landing. When the shuttle touches down here, it will be traveling at 216 miles per hour. Right now it's going more than 17,000 miles per hour. Before it lands, it must slow down, lose energy, and it must survive the intense heat caused by traveling through the atmosphere at such a high rate of speed. Several S-turns or roll reversals are used to slow down and maneuver Columbia through the atmosphere. This one is done at 256,000 feet when it is traveling at more than 26 times the speed of sound. This one is done at 208,000 feet. During these two roll reversals, entry heating is most severe, with temperatures reaching 2,500 degrees some places on the vehicle. The aluminum skin will melt at 320 degrees. The silicate tiles must insulate the vehicle from the tremendous heat. Since there is no test facility on Earth to simulate the aerodynamic and structural environment Columbia is in right now, only calculations could be used to predict what would happen during this phase of the flight. The predictions and calculations had to be right.
Columbia's here.
Hello, Columbia. Houston's here. How do you read?
Flying clear, and we're doing Mach 10.3 at 180 AS.
And we couldn't agree more, John. Your state vector's good. We've got good data in-house.
Okay.
The entry trajectory, velocity, and position look good. Columbia is heading for home, now only 470 miles away.
More left RCS, but okay.
Right, we're showing a roll. And John, we're showing you rolling right. Looking good.
Right, normal roll.
We're showing crossing the coastline flag.
Columbia, we show you crossing the coast now.
Right, yeah. We can go.
The shuttle is first sighted at about 100,000 feet with a long-range camera from Anderson Peak, California.
What a way to come to California.
And flight photo, I still look perfect right on the nominal.
Roger that. Out of 112K, 4.8 Mach.
We're seeing this in a row.
We see Del as 21 degrees.
A roll reversal is done over Bakersfield, California.
Oh, that's beautiful.
Chase has a tally.
Roger, taking.
And we're seeing 1.3 Gs coming around the hack.
Roger that.
The astronauts are making the final turn to line up with the runway.
Columbia, you're really looking good. Right on the money. Right on the money. And turning on to final, your winds on the surface are calm.
Back on the wind.
You're right on the glide slope, Columbia.
Clear, John.
Looks real good underneath. Everything looks real good.
Chase reports no tile or other damage is evident underneath the shuttle. Columbia's altitude is now just over 5,000 feet.
Pretty clear.
Without power, Columbia must land. It cannot make another attempt.
They're coming. You're down. Feet. 40, 30, 20, 10, 5, 4, 3, 2, 1, touchdown. Those gears, 10. 5, 4, 3, touchdown. Hook 'em off, skipper.
Columbia's on the roller.
Welcome home, Columbia. Beautiful, beautiful.
So I have to take it up to hangar, Joe?
We're going to dust it off first.
This is the world's greatest all-electric flying machine, I'll tell you that. It was super.
Okay, convoy's on its way.
Convoy launch. We'll stop on the Columbia. We'll stop.
The maiden voyage of Columbia has been a success. The astronauts and the vehicle have met or exceeded all 144 flight test objectives. The integrity of all the systems, propulsion, avionics, structural, flight control, power, and thermal, have been affirmed. John Young's comments after returning home.
I can't tell you what a tribute that is to the American working man and the American working woman, too. You can't imagine the variety of people who worked on this vehicle, from all walks of life, all capabilities and limitations. It's all due to their individual efforts. They proved that they can do the job. They proved it for the world to see. And I'm mighty proud to be associated with folks like that.
What a tribute indeed. The Columbia represents an achievement in aerospace technology and development never before realized in the history of manned spaceflight. It is our basic building block for the future.
It's what we've been trying to do for the last 10 years. We've got a vehicle with a payload performance that will allow us to do that, much cheaper than we've been able to do it before. It will immeasurably improve the defensive capability of the country. It will help develop space science and technology. When we get operational, the space shuttle will be able to do in 5 to 10 years what it would have taken us 20 to 30 years to do otherwise. We couldn't do it if we didn't have the space shuttle and that payload capability. And the sooner we do those things, the better off the country's going to be.
A revolutionary new era in space transportation has just begun. Routine access to space. Welcome to the future.
This is Saturn V, the rocket that took us to the moon. One of the biggest, most powerful precision machines ever conceived and built. But Saturn V was an expendable launch vehicle. Each could be used only once. With our nation and the free world increasingly reliant on space technology, the need to reduce costs, increase productivity, and expand our capabilities in space has become a major challenge. Recognizing the growing role space is playing in business, science, and defense, there is increasing international competition for the space dollar. In Japan and other foreign countries, launching systems are under development. The Ariane Expendable Launch Vehicle, developed by the European Space Agency, is booking payloads. And these systems all feature an expensive throwaway launch vehicle. But continued use of expendable launch vehicles is a luxury we can no longer afford. The United States has achieved and maintained the leadership in space. Our continuing presence in space is essential to our economy, to science, and to our national security. America's reusable space shuttle offers the most cost-competitive and versatile transportation system for the routine access to and the exploitation of space. Opening the space environment to many new users, it is a vital factor in maintaining our technological superiority in this competitive world. To compare costs in today's dollars, it takes an average of $22 million to put a satellite into orbit with a Delta expendable launch vehicle. The cost of orbiting that same satellite in the space shuttle will be around $10 million in a shared flight. This is a major step in reducing the cost per payload of spaceflight. The space shuttle is the keystone of the United States space transportation system. A fleet of 4 shuttles is planned, each designed to fly at least 100 Earth orbital missions. The shuttle consists of 3 major components. First, the orbiter, most simply described as a space-going cargo vehicle, at home in the vacuum of space or in the atmosphere of Earth. It will carry a flight crew of from 2 to 7 men and women. In its 60-foot-long, 15-foot diameter payload bay, it will eventually carry cargo weighing up to 65,000 pounds. Second, the external tank, holding over 1.5 million pounds of liquid propellant to supply the orbiter's main engines. The third major component, twin solid rocket boosters, which produce a combined thrust of over 5 million pounds for liftoff. In a typical shuttle mission, the 3 liquid-fueled main engines and the 2 solid rocket boosters will ignite, providing a combined thrust of 7 million pounds to lift the shuttle toward orbit. Two minutes later, the solid boosters will burn out, separate from the external tank, then parachute to a water landing and recovery in the Atlantic Ocean. The boosters will be refurbished and returned to service on a continuing basis. The orbiter's main engines, fed by the external tank, will burn for approximately 6 more minutes. Shortly before achieving orbit, the main engines will shut down and the external tank will be jettisoned. This empty metal shell will not be recovered, but will fall harmlessly into a remote ocean area. The orbiter will continue into orbit, powered by the engines of its orbital maneuvering system, which are fed with liquid propellant from onboard tanks. The orbit can be varied from 115 to 350 miles in altitude, depending on individual mission requirements. In orbit, many types of missions can be performed. Up to 4 satellites can be deployed on a single flight. Satellites can be repaired in orbit, refurbished or retrieved and returned to Earth. Satellites are now observing the Earth, providing valuable information for the utilization of the resources of our planet. Space probes can be placed in Earth orbit, then launched on deep space and interplanetary missions. Already we have sent unmanned spacecraft to and beyond the planets. We have seen the swirling atmosphere of Jupiter and discovered another of its moons. We have plunged through the rings of Saturn, and we have seen volcanoes erupt on the alien moon called Io. The space shuttle will expand the effectiveness of these programs while reducing costs. In its payload bay, the orbiter can carry Space Lab, a modular manned scientific laboratory designed and built by the European Space Agency for use by the international scientific and industrial communities. Ready access to the zero gravity and vacuum of space will open this environment to industry, to investigate the production of new materials, highly pure chemicals, new crystal growth methods for electronics, new metal alloys, new and lower-cost pharmaceuticals. To stimulate the commercialization of space, NASA and McDonnell Douglas Astronautics Company are engaged in a joint venture to develop a new technique in pharmaceutical processing in space, to produce substances we cannot create in sufficient quantity or purity in ground-based facilities. With completion of the mission, the orbiter's payload bay doors will be closed and latched for re-entry. The crew will fire the engines of the orbital maneuvering system to leave orbit and re-enter the Earth's atmosphere. During atmospheric entry, surface temperatures on portions of the orbiter will reach up to 2,800 degrees Fahrenheit. Once through the heat of entry, the orbiter will fly like an airplane, an unpowered, high-speed glider. This is a flight of the test vehicle, the Enterprise, the pathfinder for orbiters to come. These approach and landing tests were successfully conducted in 1977 at NASA's Dryden Flight Research Center in California. After the returning orbiter lands, it will be readied for its next flight. The era of the space shuttle is about to dawn, but it didn't come about without great effort. In 1971, the need for lower-cost transportation into space on a routine basis was recognized. NASA was given the charter by the President and by Congress to design and build a reusable space shuttle. It meant establishing a team of government and private industry, a national network of contractors. To design and build the orbiter, a prime contract was awarded to Rockwell International. In turn, over 300 subcontractors produced many of the sections and systems that comprise this complex vehicle. Final assembly of the orbiters is completed at Rockwell plants in Southern California. In New Orleans, Martin Marietta builds the external tank. This 154-foot-long structure, with a diameter of just over 28.5 feet, contains over 1.5 million pounds of liquid hydrogen and liquid oxygen propellant at liftoff. Constructed of aluminum, its outer surface is coated with both spray-on and ablative insulation to help maintain the propellant at the proper temperature, minus 320 degrees, to help prevent ice from forming on the cold outer skin before ignition, and to protect the tank from atmospheric heating during ascent. The external tank for the first shuttle orbital flight test was delivered to the Kennedy Space Center in Florida on July 6, 1979. Thiokol Corporation in Utah is responsible for development of the solid rocket boosters, the largest solid propellant rockets ever built. Each is just under 150 feet long and over 12 feet in diameter. Constructed of weld-free, high-strength steel. Each rocket motor generates 2,650,000 pounds of thrust at sea level. Although this will be the first application of a solid propellant rocket as a primary launch vehicle for United States manned spaceflight, the technology is well developed and understood. The boosters for the first flight test have been delivered. They were received at the Kennedy Space Center in September 1979. To build the solid rocket boosters alone, contracts were let to 64 companies in 20 states, and this is just one of the 3 major shuttle components. In all, building the shuttle requires 50,000 people working for hundreds of contractors in 47 states. The space shuttle is a major development in high technology. 2 specific areas have produced the greatest challenge, pushing ahead the state-of-the-art. 2 areas that have proved to be the pacing items for the first orbital flight test of the shuttle. Because of significant problems in these areas, major delays have occurred in the shuttle program. First is the development of the orbiter's main rocket engines. For their size, these liquid propellant engines are the most powerful ever built, producing 375,000 pounds of thrust at liftoff. This much thrust is generated by achieving an extremely high chamber pressure, 3,000 pounds per square inch, a major step forward in rocket technology. Besides containing such high pressures, the engines are lightweight and capable of being throttled down to 65% of thrust to control G-loadings on the shuttle during ascent. And they have been designed to perform at least 55 flights with minimum maintenance, another goal never before achieved in rocket engine design. Development of these new engines is the responsibility of the Marshall Space Flight Center in Alabama. To date, well over 500 tests have been run. While problems encountered were not totally unexpected in such a complex high-technology project, some did lead to program delays. When the flight configuration of 3 engines was run, some failures occurred which resulted in major slips in the schedule. One by one, the problems have been isolated and eliminated. Most were associated with the tremendous pressures and vibration levels which are developed. One significant contributor to these program delays was the inadvertent use of the wrong grade of welding wire in construction of the engines. This caused weaknesses in the welded areas, leading to failure under high-stress conditions. With the detection and correction of these problems, and with continual upgrading of the main engines, the 3 engine clusters have now begun to perform as planned. 4 successful firings, simulating the length and conditions of launch, at 100% of their rated thrust, have been conducted without incident. More than 70,000 seconds of the 80,000 seconds required firing times for flight readiness have been accomplished. The main engines for the first orbital flight test have been upgraded on a continuing basis. Previously stored at the Kennedy Space Center, they have been returned to the test stands in Mississippi for requalification prior to the flight. Another critical area of development which has contributed to program delays is the shuttle's unique thermal protection system. This is presently the pacing item in preparing for the first orbital flight. The thermal protection system is planned to be reusable over 100 flights with minimum maintenance. During re-entry, temperatures on the orbiter's surface will range from 400 to 2,800 degrees Fahrenheit. The temperature of the orbiter's aluminum skin must be kept below 350 degrees. Where surface temperatures will range from 2,300 to 2,800 degrees, reinforced carbon-carbon is used. However, this material is heavy and its use must be limited. Where temperatures will not exceed 750 degrees, coated Nomex fabric covers the aluminum. The major problem has been in providing thermal protection in the mid-range, from 750 to 2,300 degrees. A silica fiber material was developed for this purpose. It is a cast material containing about 93% void. It weighs only 9 pounds per cubic foot, about the density of balsa wood. Bonding of the tile to the orbiter has presented a major problem and program delay. It was determined that for attachment to the orbiter, the optimum size of the tiles is about 6 by 6 inches. 30,922 individual tiles are shaped to fit the contours of the orbiter. To alleviate stresses between the tiles and the aluminum skin, a flexible Nomex pad is mounted between the skin and the tiles. Where a stiff area of pad is joined to a lower strength area of tile, the tile tends to crack and loosen when stress is applied. Under tests, some failures have occurred at 50% of the tile's rated strength. To correct this, the bonding surfaces of the new tiles are strengthened with a substance that penetrates the tile about 1/10 of an inch and provides a thin layer of high strength for bonding to the Nomex felt pad, thus eliminating the problem. Tiles on the orbiter Columbia are being tested to assure the quality of the bond between the tile and the spacecraft. Tiles failing these tests, or that are in any way deemed questionable, are removed and replaced with strengthened tiles. During testing through the first quarter of 1980, over 15,000 tiles were tested and over 3,000 removed and replaced. Testing and bonding are proceeding at a rate which should allow completion by the end of summer 1980. The thermal protection system is showing good progress. The Columbia is being readied in the orbiter processing facility for an early fall rollout. The solid rocket boosters and external tank are in the vehicle assembly building at the Kennedy Space Center, awaiting the Columbia. The orbiter main rocket engines are performing to specifications and are no longer a pacing item. Launch Complex 39 has been modified for shuttle use and is ready. The Launch Control Center has been adapted for the shuttle. Staffing for an Apollo launch required 465 people. Only 100 are required for shuttle launches. The 15,000-foot-long landing strip at KSC will be the primary landing site for operational flights. The first orbital flight tests will land on the 11-mile-long lake bed at Edwards Air Force Base in California. and the orbiter processing facility is in full operation. The second orbiter in the shuttle fleet has already served as a structural test article and is now being reconfigured for flight. The airframe and aft fuselage are undergoing the necessary modifications. One half of the crew module component has been completed. Delivery date for the completed orbiter is the summer of 1982. Detailed component fabrication for the aft fuselage and crew module of the third orbiter has been underway for about a year. Soon, work will begin on the lower forward fuselage. Delivery is set for the fall of 1983. At the Johnson Space Center near Houston, 26 veteran astronauts and 35 new astronauts are being trained as pilots and mission specialists for the coming shuttle flights. Crews for the orbital flight tests are undergoing specific mission training. The crew of the first flight is astronaut John Young, commander, and veteran of 2 Gemini and 2 Apollo missions, and Robert Crippen, pilot. Included in this training are mission simulations in the shuttle simulators, which are linked to the Mission Operations Control Room, from which flights will be controlled. A second control room is being prepared for the exclusive use of the Air Force for control of Department of Defense flights from the Kennedy Space Center in Florida and later from Vandenberg Air Force Base in California. Construction at Vandenberg began in 1978, with excavation completed in late 1979. Site preparation and construction are expected to begin in mid-1980. This phased-by-year military construction program is aimed at an initial shuttle launch from Vandenberg by mid-1984. As the shuttle nears its first flight test, members of the industrial, scientific, and defense communities are standing by. Of the 39 flights scheduled in the first 3 years, 35 are presently reserved for NASA, the Department of Defense, commercial, foreign, and military payloads. 152 separate payloads, which include 76 small, self-contained payloads, are already booked to take advantage of this economical and versatile means of space transportation. The Department of Defense has urgent requirements for the shuttle. Should the shuttle not be available, the redesign of payloads meant for the 60 by 15-foot payload bay to the lesser capabilities of expendable launch vehicles would be a formidable and expensive task. The shuttle is nearly ready for its first orbital flight test, scheduled between November 1980 and March 1981. In the 1980s, we will expand the utilization of space, and space flight itself will be quite different from our previous era of space exploration in the 1960s and 70s. We stand at the beginning of a new and practical era in space technology. Spaceflight has become a necessity of modern civilization, essential to our economy, to scientific achievement, and to our national security. The space shuttle is the means by which we will maintain the leadership in space that we have achieved over the last 2 decades.
It was a year of preparation, especially for the reusable space shuttle. Astronomers were able to point an orbiting telescope at stars while aiming and making corrections much like ground-based observatories. Pioneer spacecraft arrived at Venus and landed on that planet's shrouded surface. The Voyagers continued their journey toward Jupiter and Saturn. With the Department of Energy, NASA built a wind generator for a small New Mexico town. And in aeronautics, a wide range of research projects to improve both general and commercial aviation. If all goes according to schedule, scenes like this, a reusable space shuttle making its final approach to land, will be a common sight beginning next fall. Many of the tests and much of the training to prepare for that historic first flight took place in 1978. 47-year-old John Young, veteran of 2 Gemini and 2 Apollo space flights, will be commander for the first manned shuttle mission. Here, he practices making landings in a space shuttle simulator at the Johnson Space Center with Robert Crippen, the 40-year-old astronaut who will fly with Young as pilot. Anticipating the space shuttle's flight schedule in the years ahead, NASA selected 35 new candidate astronauts in 1978 to begin training as shuttle mission specialists and pilots. The 35, including 6 women, were chosen from nearly 8,000 applicants and will be training until mid-1980. Enterprise was flown in its now familiar plane-on-plane berth from California to NASA's Marshall Space Flight Center in Huntsville, Alabama. For the first time, all the major components of the Space Shuttle Transportation System came together for testing. When completely assembled, the shuttle orbiter will sit astride 2 recoverable solid rockets and atop a giant external fuel tank. The entire system was subjected to vibrations similar to those that will occur at launch. At the Thiokol Corporation facility in Utah, a shuttle booster that will produce about 2.65 million pounds of thrust at launch was successfully test-fired again. Each of the Space Shuttle's 3 main engines that will provide the orbiter with its primary power from launch pad almost to Earth orbit were also successfully tested. Work is continuing on the second shuttle orbiter at the Rockwell plant in California. This is the spacecraft that will actually make the first flight with astronauts Young and Crippen at the controls. Looking farther ahead, Marshall Space Flight Center engineers have been studying problems that astronauts may face during future shuttle missions, and they are doing it underwater. This is one of the few ways that near weightless maneuvers can be practiced here on Earth. 1978 was a very busy year for space science. One of the most ambitious missions involved 2 Pioneer spacecraft that were launched toward a rendezvous and landing on this planet, Venus. Scientists believe that by studying the weather of Venus, they can learn about our weather here on Earth. The Pioneer orbiter spacecraft is programmed to circle Venus every 24 hours, studying the upper fringes of the Venusian atmosphere as it travels along. The second spacecraft, the multiprobe, is made up of a space bus with 4 data-gathering spheres that plunge down simultaneously to different parts of Venus, returning valuable information about its 900-degree surface and carbon dioxide environment. This is a computer representation of the atmosphere of Jupiter. 2 unmanned Voyager spacecraft are en route to Jupiter now. The first Voyager will reach the planet in March 1979, followed by the second spacecraft 4 months later. Then, on to Saturn. At the time of closest encounter, on November 12, 1980, Voyager 1 will have traveled 1.4 billion miles through space. The Voyager missions make it possible for scientists to go back in time and sample the conditions from which the Sun and planets, including the Earth, are believed to have formed. IUE, International Ultraviolet Explorer, is a telescope in space which is operated effectively in real time by astronomers on the ground. Visiting astronomers at the Goddard Space Flight Center can have the telescope pointed, decide what data to take, and modify their measurements as they observe. With craft like IUE, scientists can begin thinking in terms of observatories in space as facilities. Also launched in 1978, the second in a series of high-energy astronomy observatories, HEO-2. The 7,000-pound spacecraft carries a large X-ray telescope with 4 major experiments which can be pointed at specific objects to study them in detail. The high-energy explorers are giving astronomers a different view of our universe and helping us to better understand it. The Space Telescope moved through another manufacturing phase this year at the Corning Glass Works in upstate New York and is scheduled for deployment by the Shuttle Orbiter in 1983. Looking from space with instruments in space, we can see the universe in ways that are impossible from the ground, bringing us closer to even greater discoveries in cosmic astronomy. There was continued and increased emphasis on applications in 1978. Landsat 3, a remote sensing spacecraft, was orbited. Efforts like these over the next decade will try to develop a capability to watch and understand what's happening on the surface of the Earth, land, and water, and to put all that data together in such a way that it can be used as management information for the global environment. Before its so far unexplained short circuit, the first CSAT collected data for 99 days. What it returned during that time were images of sea ice, waves, coastal conditions, and various landforms. It also measured sea surface wind speeds and temperatures. Project scientists expect it will take more than a year and a half to process the data collected by CSAT. This is Beth, a perfectly healthy child of a NASA employee at the Johnson Space Center in Houston, Texas. She is shown here testing out the fit and mobility of an isolation suit that can be used by a youngster with a rare disorder known as severe combined immune deficiency disease. Because of his inability to fight off even the most common germs, 7-year-old David has had to be confined in sterile isolation since birth. The NASA-developed isolation suit now allows David to get out and at least do some of the things normal children enjoy. Ben Abruzzo and Maxie Anderson, two of the 3 men that crossed the Atlantic using a helium-filled balloon, stopped by the Goddard Space Flight Center to meet some of the people who monitored their flight with the help of the Nimbus 6 satellite. On their first attempt, the Nimbus 6 beacon made it possible to alert air-sea rescue when they became lost in a heavy storm. So for the second try, Ben Abruzzo said they decided to take along an extra beacon.
On the second flight, because of the fact that we knew that the only link we had with the world on the first flight was the satellite transmitter, we had 2. And again, the information came to us in flight telling us of our course and our position. It confirmed the weather data that our base station had and allowed us to change altitudes properly so that we were able to complete the flight successfully. And in fact, on the tail end of it, we changed altitudes and vectored ourselves onto a very close destination proximity of Paris.
Last January, the first large operational wind generator to be used in the United States in several decades began producing electricity. The place, Clayton, New Mexico. Population, about 2,900. The project is funded by the Department of Energy and managed by NASA's Lewis Research Center in Cleveland. The 100-foot-high wind generator is capable of producing 200 kilowatts that feed directly into Clayton's utility system, about enough to electrify 60 homes. The research is aimed at improving performance and helping determine the future cost of electric power generated by wind systems. In aeronautics, the emphasis is on basic research and basic technology, preparing the way for future advances in aviation. At the same time, NASA continues to develop technologies to the point where industry can take them up. One of the major research efforts involves using full-scale wind tunnels and other facilities to improve crop dusting aircraft. Studies of how spraying is affected in the wake behind the airplane, handling qualities, fuel efficiency, and overall airplane performance are the goals. See those vertical fins on the wingtips of this small business jet? Those are called winglets, and they were invented by Dr. Richard T. Whitcomb of NASA's Langley Research Center. What the winglets do is reduce the drag on the plane as it moves through the air, saving fuel in the process. Just about any plane can benefit, from the largest jet cargo tankers to small cross-country planes like this one made for the home-built market. Again and again, engineering research pilot Jim Patton forces his single-engine plane into a stall spin. What he and the data-gathering engineers on the ground are trying to do is improve the design for wings and tail sections of airplanes to make them more resistant to stall spins. This type problem accounts for about 30% of crash fatalities in small private airplanes. Combinations of wind tunnels, simulators, radio-controlled model flights, and full-scale tests are used to gather the needed data. This is an experimental XV-15 tilt-rotor aircraft being put through its paces in the 40 by 80-foot wind tunnel at NASA's Ames Research Center. The plane's engines are designed to tilt from vertical to horizontal in mid-flight, making it possible for the craft to take off, hover, and land like a helicopter, and it can cruise at the speed of a fast subsonic airplane. This research is an attempt to develop more economical short-haul intercity transportation. At Ames, they are also flying this experimental jet called the QSRA, meaning Quiet Short-Haul Research Aircraft, a plane that can operate at lower noise levels than most of today's small aircraft, carry the same payload as a 727 jet, and be able to land on a runway as short as 1,500 feet. At the Lewis Research Center, engineers are working to reduce noise and air pollution on aircraft engines that will one day be used for short-haul commuter-type planes, aircraft in the 300 to 500-mile range, which customarily land at smaller airports. To move ahead in research and development and plan the aircraft of 15 to 20 years from now, NASA's Dryden Flight Research Center in California has been test flying the YF-12, an airplane that cruises at 3 times the speed of sound. Being studied are heating, flight stability and control, and structural dynamics, all factors that have great impact on the design and performance of future aircraft. There were 2 anniversaries in 1978 that need to be noted. 75 years ago, Orville and Wilbur Wright made the first successful powered flight in an airplane. It was also just 20 years ago that the space program officially began, an extension of the basic Wright brothers flight. 1978, a year of progress in both aeronautics and space research. This special report brought to you by NASA, the National Aeronautics and Space Administration.
Columbia, you go for APU pre-start.
The Space Shuttle, our key to the routine and economical use of space for scientific, defense, and commercial purposes. The orbiter is a space-going cargo vehicle, which will return to Earth and land like an unpowered airplane. It will carry a crew of from 2 to 7 men and women. It can achieve orbital attitudes of up to 350 miles. In its 60-foot by 15-foot payload bay, it will eventually carry cargo up to 65,000 pounds into low Earth orbit. To lift this massive vehicle into orbit, to allow it to maneuver while in orbit, and to bring it back to Earth, it takes power. The raw thrust of rocket propulsion. There are 4 separate propulsion systems on the shuttle. Twin solid rocket boosters support the orbiter and external tank on the launch pad and provide most of the thrust for the first 2 minutes of liftoff and flight. The main propulsion system, a cluster of 3 liquid propellant rocket engines mounted aft on the orbiter. The main propulsion system is supplied liquid hydrogen and liquid oxygen from the external tank. The orbital maneuvering system, mounted in 2 pods on the aft fuselage, produces propulsion for the final stage of ascent, major orbital maneuvers, and retrofiring for descent. The reaction control system, consisting of 44 small rocket engines mounted in clusters in the nose section and in the 2 rear pods, provide thrust for aligning the shuttle while on orbit. The solid rocket boosters are the largest of their kind ever built, nearly 150 feet long and over 12 feet in diameter. They are also the first built for use on a United States manned spacecraft and the first designed for reuse. The solid propellant is contained within the booster casing. It looks and feels like the hard rubber of a typewriter eraser. The boosters are assembled from 4 seamless segments of half-inch steel, lined with heavy insulation. After ignition, the motor is up to full operating pressure in less than 1 second. Each booster generates a thrust of nearly 3 million pounds at liftoff. The main propulsion system represents a major technological advancement in engine design. In the past, rocket engines were usually used only once. These are the first engines designed for reuse, to be flown on 55 missions before needing a major overhaul. For their size and weight, the 3 main engines are the most powerful ever built, each producing 375,000 pounds of thrust at liftoff. A space shuttle main engine has an internal chamber pressure of 3,000 pounds per square inch, 4 times that of previous rocket engines. The thrust can be varied from 65 to 109% of rated power to tailor engine performance for different payload weights, to keep acceleration rates within comfortable bounds, and to give additional thrust for contingency situations. The 3 main engines can swivel 21 degrees up and down in the vertical position and 17 degrees from side to side to steer the vehicle during flight. The liquid hydrogen and liquid oxygen these engines use for propellant is contained in the external tank. This structure is just over 154 feet long, with a diameter of nearly 28 feet. It is constructed of aluminum alloy, up to 2 inches thick. It is actually 2 propellant tanks connected by a cylindrical collar called an inner tank. The forward tank holds 140,000 gallons of liquid oxygen at minus 297 degrees Fahrenheit. The aft tank holds 380,000 gallons of liquid hydrogen at minus 423 degrees Fahrenheit. These tanks feed propellants to the main engines through fuel lines almost 1.5 feet in diameter. The tank is covered with insulation to help keep heat from reaching the propellants and causing excessive boiling, and to prevent ice from forming on the outer surface during launch preparations.
17, guidance release, 15, 14, 13, 12, 11, 10, 9. We have ignition sequence start.
When the main engines have reached 90% of full thrust, the solid rocket boosters will ignite and the shuttle will lift off. A combined thrust from all engines of over 7 million pounds, pushing it toward orbit.
Firm roll, bud. Roger, on a roll.
Just under a minute into the flight, the thrust of the solid rocket boosters will be reduced by approximately 1/3, achieved by a change in the shape of the solid propellant. This, plus throttling down the main engines, will keep stress and atmospheric heating on the shuttle within safe limits. 2 minutes into the flight, the boosters will burn out and be jettisoned.
Okay, SRB SEP at 212. SEP flight. Roger, SEP.
They will parachute to a water landing.
Output bias on RGA4 and the roll axis, no problem at this time. We're also seeing an error in IMU2C.
To be recovered and prepared for their next flight.
Columbia, we have a data
After the solid rocket boosters separate, the orbiter and external tank, with engines still firing, continue to near orbital velocity at about 70 miles above Earth. The main engines will burn for 6 more minutes, then cut off. Almost 1.5 million pounds of liquid hydrogen and liquid oxygen have been consumed during the first 8 minutes of flight. Now the external tank will be jettisoned and fall into a predetermined ocean area, the only major component of the shuttle vehicle not recovered for reuse.
Okay, Houston, we're at nominal target.
After the main engine shut down, the 2 engines of the orbital maneuvering system ignite. Each delivers 6,000 pounds of thrust for the final portion of ascent into Earth orbit. During the mission, these engines will be used for such major maneuvers as circularizing the orbit, rendezvous with other orbiting spacecraft, changing orbits, and finally for the burn out of orbit and return to Earth. The fuel the orbital maneuvering system engines burn is contained in tanks within the aft pods. This fuel is hypergolic. When mixed together, it ignites. The combined thrust of the orbital maneuvering system engines is 12,000 pounds. Once in orbit, the reaction control system will control the attitude of the orbiter and be used to make very small maneuvers. There are 38 main thrusters with an output of 870 pounds each, and 6 vernier thrusters delivering 24 pounds each. In the nose section is a cluster of 14 main and 2 vernier thrusters. In each rear pod, a cluster of 12 main and 2 vernier thrusters is located. The reaction control system uses the same type of propellant as the orbital maneuvering system. A crossover network enables propellant to be transferred from one system to the other. The reaction control system will be used to bring the orbiter to the correct attitude for entry. The orbital maneuvering system will be used to reduce the orbiter's speed and bring it down into the Earth's atmosphere. During the entry phase, atmospheric friction on the orbiter, slowing from an orbital speed of about 18,000 miles per hour, will generate surface temperatures of up to 2,600 degrees. To maintain the correct attitude during this critical portion of the flight, the reaction control system will be used. Once through the heat of entry, the orbiter becomes a glider, using aircraft-type controls. The jobs of the propulsion systems are finished. Until the next flight.
10 knots, 200 knots, 190 knots. Speed brakes are tracking.
Down.
That was a super one.
The orbiter will be the approximate size of a 727 jet airliner, and the entire vehicle, except for leading edges, will be covered with reusable surface insulation. This insulation will be a coated porous material in tile form, consisting of rigidized high-purity silica fibers in an amorphous silica binder. Obviously, the number of tiles to be installed over the entire surface of the vehicle, with its varying contours, protrusions, and openings, requires innovations in technology. The building block concept developed by the Space Division is a method of tile installation by which less complex areas, which make up 70% of the vehicle surface, are covered with common tiles. These tiles are tailored to thickness after receipt from the subcontractor and are installed in sectorized gross areas. The building block concept allows maximum use of common tiles and lessens the necessity for exact locations which would be required to install tiles of discrete design. Space Division is using a DC-3 airframe to aid in development of tile installation procedures. It serves as a low-cost test article and provides contours which are similar to those that will be encountered on Shuttle. After being machined, the tiles will be pre-fitted to the vehicle bond surface to control surface steps and gaps. A strain isolator pad, known as the SEP, is adhesive bonded to the tiles. The SEP is made from a no-mix felt and is used to accommodate the strain caused by the differences in coefficients of expansion of the silica tile and the aluminum vehicle structure. A room temperature curing silicone adhesive is then applied to the surface of the vehicle. The tiles are installed in arrays covering areas up to 35 square feet at one time. The reusable surface insulation, when fully developed, will provide a reliable, cost-effective, lightweight thermal protection system for Shuttle, and will help in the realization of this low-cost workhorse space transportation system to be operational by 1980.
3,000 miles range to go. CRT displays look good.
This research pilot is simulating a landing of the reusable space shuttle. The shuttle is a cargo-carrying combination, spacecraft and aircraft, able to carry large payloads to and from Earth and space 100 times or more. It's scheduled for use in the early 1980s. One of the men who'd like to fly the shuttle is astronaut Joe Engel. Here at the Space Division of Rockwell International in California, he describes a full-scale mock-up of the big craft.
What we think of as the airplane part of the shuttle, which is what you see right behind me, is 122 feet long. That's about the same size as a DC-9. It has a wingspan of 88 feet, and probably it's a little bigger around than a normal cargo-carrying airplane.
A typical mission starts with a vertical launch. After use, 2 solid rocket booster engines are jettisoned and recovered by parachute. Once in Earth orbit, the shuttle will conduct experiments or rendezvous with satellites, whatever the mission is.
Enterprise Houston.
Go ahead, Demo.
We have a couple of updates to your pre-flight Q card, the altitudes.
Okay, stand by one. Okay, we're ready to copy.
Separation is at 23.0. Next one, 18.0. Rolled out on final at 8.3, and then 1.9er. I'd suggest you go ahead and start your engines and begin your taxi.
It's called Enterprise, first of the Space Shuttle orbiters, the beginning of a new space transportation system. A craft that can carry up to 65,000 pounds into space and land back on Earth like an airplane. 5 times, 2 astronauts were carried piggyback atop this 747 jet and released. 5 times, they brought the huge spaceship in for powerless landings.
Okay, the gear is coming down at 270. Gear coming. Doors open and they're all down, coming down. Look down here. 50 feet. 40 feet. 30. 20. Okay. 10.
Holding 10. 220 at about 5 feet.
Summing up the year's work for all 4 of the astronaut crewmen, astronaut Gordon Fullerton.
We're at the end of the approach and landing test phase of this program, but it's really not an end, it's a beginning. It's just a small step really accomplished toward getting the orbiter into space, and then in that aspect I'm looking forward to more of the same exciting times as we continue on toward that first orbital flight.
Enterprise will not be the first shuttle into space, but this one will be. Shown here being assembled by Rockwell International, it is simply designated Orbiter 102.
102 is undergoing construction right now in Palmdale, and it's scheduled to be shipped the middle of next year over to DFRC, where we'll perform a hot fire test on it. We will mate it to the 747 and fly it to Florida in preparation for launch into orbit in March of 1979. After about 24 hours in orbit on 102, it also will land here at DFRC on the lake bed in the manner similar to the test flight that we've just completed on the approach and landing test.
Also completed this year, the 154-foot long, 27.5-foot wide external fuel tank for the shuttle. Designed and assembled by Martin Marietta at NASA's Michoud Assembly Facility near New Orleans, the external tank will fuel Shuttle's 3 main engines on the way to orbit. Another major milestone for the new space transportation system was the successful test firing of one of the 2 Thiokol solid rocket motors that will also help boost the shuttle orbiter into space. This animation shows how they work during launch. The 2 solid rocket boosters strapped to each side carry their own propellants and burn for about 2 minutes before separating. Their onboard parachutes will then bring them back to Earth for recovery and reuse. The large external fuel tank continues feeding the shuttle engines for an additional 6 minutes, separating just before the shuttle reaches orbit. This is the only part of the shuttle system that will not be used again. When NASA announced it was recruiting between 30 and 40 new astronauts, more than 8,000 hopeful candidates responded, including over 1,500 women. The Johnson Space Center in Houston is in the final screening process to select from this group both mission specialists and pilots for future space shuttle flights. To get a feel for handling large structures in space, engineers at the Marshall Space Flight Center have been practicing underwater, the closest you can come for long periods of time to simulating the weightlessness of space. It's anticipated that the shuttle will make the building of large space structures possible, as well as the assembly of heavier satellites and instruments to better observe Earth and provide improved communications. Even solar satellites could be constructed to beam the sun's energy to Earth if it becomes an economic and reasonable alternative to some of our ground-based energy resources. Many of the early shuttle flights are already booked with confirmed payloads, according to NASA's Director of Pricing, Launch Agreements, and Customer Engineering Services, Mike Smith. This payload section of a shuttle under construction gives some idea of the space available.
On Earth. Well, we're sold out on flights through 1980 and have firm flight assignments through 1981. Typical of these flights are the launch of a long-duration exposure facility for NASA on Flight 7 and its retrieval on Flight 17. We have a full manned space lab flying on Flight 11 and a Jupiter orbiter probe flying on Flight 26. We have numerous communication satellites being launched for Telesat Canada, ComSat, Satellite Business Systems Corporation, and India in the early 80 and 81 time period.
Manufacture of the first flight unit has begun on Spacelab, shown here in mock-up. Spacelab is unique because it represents a cooperative venture by NASA and the European Space Agency. To be built in self-contained modules, the Spacelab will be placed inside the shuttle payload section. There, from 1 to 4 payload specialists will attend to a variety of experiments while working in a shirt-sleeve environment. Space Lab is expected to make significant contributions to science, medicine, industrial processing, and other fields. In space science, 2 unmanned Voyager spacecraft like this are now on their way toward the planets Jupiter and Saturn. Their journey could last over a decade, with investigations of more than a dozen major planetary bodies, including Uranus. The program is designed to yield valuable new information about the origins of the solar system and formation of the Earth. One of the ways it will do this is with pictures. Dr. Bradford A. Smith is Associate Professor of Planetary Sciences at the University of Arizona and team leader of the imaging experiment on Voyager.
We begin our observations of both Jupiter and Saturn approximately 100 days before we arrive at the planets themselves. During that period of time, we're constantly looking at the planet. Each planet, both Jupiter and Saturn, rotates in approximately 10 hours. So every 10 hours, as we're approaching these planets, over that 100-day period, we will see the whole surface of the planet rotating beneath us. As we get closer and closer, the resolution gets higher. We see smaller and smaller features. And as we get very close, we finally get so close that we can't see. We don't have enough pictures to cover the entire surface of the planet. But we will select out particular features of great interest observed during that so-called observatory phase, and these features will be targeted for close examination as we fly by.
The Voyagers will eventually leave the solar system, each carrying a cosmic greeting card in the form of a copper record. Called the Sounds of Earth, they were assembled by a group of prominent scientists and educators. The record begins with 115 photographs and diagrams in analog form that describe mathematics, chemistry, geology, and biology of Earth and our location. The pictures are followed by spoken greetings in 60 languages.
Shalom. Hola y saludos a todos. Selamat malam hadirin sekalian.
Hello from the children of planet Earth.
The sounds of weather, surf, birds, and other animals, and almost 90 minutes of music from around the world. Finally, here in part, is the text of a printed message from the President of the United States on the chance that someone is out there. This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours. We hope someday, having solved the problems we face, to join a community of galactic civilizations. This record represents our hope and our determination and our goodwill in a vast and awesome universe. How stars produce the energy that makes them burn so bright, and then how they transmit this energy through millions of miles of space, losing very little intensity along the way, is of great interest to scientists. To study the stars, HEO-1, High Energy Astronomy Observatory, was launched in August. Already, HEO's instruments have found a gigantic star whose X-ray radiation increases violently over a period of time, then returns to normal. HEO-1 will be joined in its task of mapping the sky for X-ray sources by 2 other observatories in the future. NASA continued applying the technology and science learned in space to improve systems for managing the Earth and managing our business here on the ground. This includes further use of our remote sensing capabilities, which enable us to look at the whole Earth or large regions of the Earth in ways not previously possible. Landsat satellites 1 and 2, for instance, are helping us understand the condition of agricultural crops, forests, and groundwater, observations that make it possible to predict and manage more efficiently. Most of NASA's launches this year were paid for by other users in other countries. These included launches for the European Space Agency, Japan, Indonesia, and Italy. Not all the launches were successful, however. Both a Delta and an Atlas rocket failed shortly after liftoff, the first unsuccessful launch in 3 years for the Delta and since 1975 for the Atlas. More and more, NASA is working with other government agencies, such as the Department of Energy. NASA's understanding of rotating machinery, solar cells, and heat transfer is being applied to the development of windmills and better turbines. The Lewis Research Center in Cleveland, for example, is gathering information on as many electric vehicles as possible and is also working to improve nickel zinc batteries. NASA is also applying solar energy technology to new developments that may bring it into effective use as part of the National Energy Program. Efforts to apply technology to make aviation safer, more economical, cleaner, and quieter continued this year at several NASA field centers. Energy efficiency to curb airplane fuel consumption has high priority. Areas of study include engine research, improved shapes, computerized flight control systems, and lighter, stronger aircraft structures. These crash tests at the Langley Research Center are an attempt to find out what happens when a general aviation airplane does just that. The highly instrumented plane and dummies should help aircraft manufacturers build even safer airplanes in the future. These spin tests look at a different safety problem, the problem of spins and stalls in general aviation airplanes. In part of the project, researchers are trying to determine the effects of tail design on spin characteristics. A new research aircraft, which combines features of both helicopters and conventional airplanes, the XV-15 tiltrotor, completed its first phase of flight testing. These short and vertical takeoff and landing aircraft may one day improve intra-city transportation. (1977), an important year for both aeronautics and space research, with much of the technology finding down-to-earth uses.
Shuttle, being developed for the United States by the National Aeronautics and Space Administration, will be the world's first reusable space transportation system. This is a full-scale mock-up of the Shuttle Orbiter. Shuttle is a combination spacecraft and aircraft that will carry satellites, laboratories, and other cargo into Earth orbit in its huge cargo bay, all for the benefit of man on Earth. Shuttle is being built now to become operational in 1980. It will provide our nation with an efficient space transportation system to serve commercial, scientific, and defense needs through the end of this century. Space Shuttle will be an important tool in providing mankind with information that will help in managing and preserving our Earth. Photography from shuttle missions will be an invaluable aid in locating new sources of oil, natural gas, and other kinds of energy. It will also help to determine the sources and the extent of air and water pollution around the globe. Earth Resources Satellite, placed in orbit by Shuttle, will map ocean surface temperatures to help oceanographers interpret current patterns and predict the movements of schools of fish. Shuttle will help to lower the cost of communication satellite operations and to improve the quality of worldwide communications. Sensor systems and satellites carried into orbit by Shuttle will help inventory crops throughout the world, detect blight and insect infestation, in many cases before they can be detected from the ground. These sensors in space can also help to conserve our forests by spotting fires in remote locations and detecting tree disease and pest infestations. Shuttle will carry satellites and sensors into space that can help to identify new sources of minerals all around the world. And Shuttle will be a reusable spacecraft. It will retrieve satellites which malfunction and either service and repair them in orbit or return them to Earth for repair and reuse. Shuttle will provide our nation and the world with routine space operating capability and wide mission flexibility. Even though Shuttle will not be operational until 1980, major space-using nations of the world are negotiating with the United States for agreements to use our space shuttle, our launch facilities, and our satellite information. Canada has already built a multi-million-dollar center to process data from our Earth Resources Technology satellite. And Italy is building an ERTS ground station. The European Space Research Organization is building a space lab to be carried into orbit and retained in the Shuttle Orbiter cargo bay. It will serve as an inhabited Earth-orbiting laboratory on missions of up to 30 days duration. Scientists will be able to perform tasks in the weightless environment of space that would be impossible on Earth. This provides a great potential for new manufacturing processes. Shuttle is already contributing to our national economy in the initial stages of development and manufacturing. Studies have shown a positive correlation between the level of space research and development and national productivity. The growth in technology that is a direct result of space activity is providing us with more and more goods and services, and is helping increase the gross national product. And as we keep finding more ways to use this technology, the benefits will continue. Our demands for energy are making our nation more and more dependent on the foreign oil-producing nations, further affecting our balance of trade. The United States exports which help most to maintain a favorable balance of trade are those to which aerospace technology has made a substantial contribution. These include American commercial and consumer lines, such as sophisticated machinery, calculators and computers, and microelectronics. These are some of our country's leading exports. These high-technology products have always been a major ingredient of U.S. world leadership. Research and development of the kind demanded by the Space Shuttle program is continuing to build this technology and contributing to a better balance of trade for our nation. Beyond this, the Space Shuttle is providing jobs and contributing to the nation's economy right now in contractor, subcontractor, and government facilities throughout the country, years before the shuttle itself will begin its operations in space. The Space Shuttle will be the cornerstone of national and international space activities for years to come, helping to manage our Earth for the benefit of all mankind.
North American Rockwell Space Division proposes to serve NASA as Space Shuttle System contractor. We want the job for a lot of reasons, and we think there are a lot of reasons why we should have it. Good reasons. We want the job because we believe in shuttle as the key to man's future in space. We want the job because building space systems for NASA is the only pursuit we have. We're dedicated right now to finishing up the job on Apollo CSM and following through on the Skylab program. We have a good team here at Space Division. It's a team built up over more than a decade of work with the space agency. We want to keep it together and go on from here. We know what it will mean to be NASA's contractor for the shuttle system. What a load of responsibility we'll carry to NASA, to the government, and to the people of the United States, even to the future of all men. Our shuttle program manager, Buzz Hello, and his shuttle management team know best of all. They've been there on programs that were stepping stones to shuttle. It means designing the vehicle so that it will meet the mission objectives. But it also means designing the overall system so that it will meet objectives of cost per flight and cost of development and production. We've submitted our proposal. It's all in there. But we want to give it added dimensions, dimensions of experience. The Navajo, first piggyback flight, first big liquid rocket booster. The X-15, going from aircraft to spacecraft and back to a controlled Earth landing. Pioneering in spaceflight control, breaking all records for manned aircraft performance. The B-70, the largest and fastest delta-wing aircraft built thus far. Pioneering with the X-15 in structures and aerodynamics and flight temperatures. Saturn S-2, an achievement in design and fabrication of cryogenic launch vehicles. And the Apollo Command and Service Modules, the first step for man in voyages through space. Neil Armstrong summed it up for us pretty well after his flight in Apollo 11.
I've been a very fortunate fella over the years. I've flown a lot of machines that many of you out here today have put together for us, including the T6 and the SNJ, B-51 and F-100 and F-86 and X-15. Those airplanes always took me out and got the job done and brought me back. And it was no surprise to me to find out that spacecraft Columbia would do the same thing.
You wanted us to redesign some of the parts on that Ohm system because the way it's
We have a
done.
background of shuttle-related experience that we can lay on the line with any company. For 3 years now, we've worked directly on shuttle with NASA, exploring, testing, learning.
We've been using 8 by 8 inch tiles.
We've come pretty far with a thermal protection system for the orbiter. Not perfected yet, but a good start toward a design that will provide the needed protection through mission after mission, yet fit into the turnaround requirements that will make shuttle economical to operate and maintain. We're learning a lot from the B-1 about production and about the kind of turnaround needed for a military system and how to design it in. To help achieve low cost per flight for shuttle, we've worked with American Airlines, learning how a commercial airline turns planes around within the tough commercial cost constraints and demands for safety, maintainability, and reliability.
I think we want to handle it much the same way that we learned to handle it on the CSM and the S2 programs, and that is...
We've considered cost, schedule, and operational effectiveness right on down the line in our proposal, including our facilities, many of which can be adapted for shuttle production and test at a minimum of cost. The use of NASA and government facilities for test and for operations. And by the way, North American Rockwell is experienced with operations in every facility proposed for shuttle test. That's it. It's what we wanted to say. We have the team with the skills, the knowledge, and the experience that NASA's shuttle system contractor needs. We have a good leg up on design and on management systems that will meet performance and cost goals. We're ready to work with NASA on selection of qualified firms around the United States to provide shuttle components and subsystems. And of great importance to our ability for follow-through on what we propose, we're backed all the way by one of the 50 largest corporations in the world, North American Rockwell.
Strong interference on subspace, Captain. The planet must be a natural radio source.
Hi, I'm Nichelle Nichols, but I still feel a little bit like Lieutenant Uhura on the Starship Enterprise. You know, now there's a 20th century Enterprise, an actual space vehicle built by NASA and designed to put us in the business of space, not merely space exploration. Now, NASA's Enterprise is a space shuttle built to make regularly scheduled runs into space and back, just like a commercial airline. The shuttle may even be used to build a space station in orbit around the Earth. And this would require the services of people with a variety of skills and qualifications. Average good health is required, and candidates will train right here at Johnson Space Center, just outside Houston, Texas. Astronaut Alan Bean has agreed to show me some of the training and evaluation that new astronaut candidates will be undergoing.
Over there during the Apollo
You're
program.
Apollo, right?
Apollo. I flew on Apollo 12, and I flew on...
Skylab, too.
Okay, you know a lot.
I know a lot about you, Alan B.
This whole Johnson Space Center is not just for controlling space missions. We got engineers that work on developing the hardware here, medical people that work on testing and the like. And then we've got some simulators over here where we train in frequently, and I'll...
As a shuttle
simulator? Yes, the same sort of thing that the new scientists, astronauts, and which we now call mission specialists, and pilot astronauts will be flying over the term that they're here. Nichelle, this is the lower body negative pressure device that we use to check and see what physical condition you're in. And if you'll get in, maybe I can explain it to you. You kind of have to put your feet down in through this opening.
It's kind of ominous.
Well, it is in looks, but it feels good when you get in there.
Okay.
And it's got to be up real tight around your body
I see.
so that it can form a airtight seal, a vacuum seal.
I see.
We're going to pump the air out of this lower body negative pressure device, and in so doing, it'll put a pull on the blood in your lower body.
What is that for? Why?
Well, what it's going to do, it's going to check what condition your heart and your cardiovascular system is in. So get ready.
The Enterprise was never like this.
No, it wasn't. Okay, you ready? How's that feel?
Fantastic.
Okay, I can come down here with these controls and change the amount of suction on your lower body to stress your heart to different levels. Want to know how to get out when the test is over?
Yeah, I think it was a good idea.
You push right on there.
Oh. I feel like we have one Enterprise that was fantasy, but now we've got the real Enterprise.
Well, this Enterprise is half real and half fantasy. Why don't you have a seat over here in the commander's side,
It
Nichelle?
looks just like my Enterprise.
Yeah, it does kind of. Well, I'll tell you what it does look like. It looks pretty much like the real shuttle orbiter.
Captain, at last.
Since you're sitting in the commander's seat, Nichelle, let me show you how you might fly it if we were in space.
Oh, boy.
Between your knees there is what we call the hand controller, the rotation controller. It operates just like a conventional airplane stick, in that if you pull back on the stick, or the hand controller, it'll raise the nose of the orbiter.
Oh, yeah.
And then if you push forward, it'll lower the nose. If you wanted to bank left for a left turn, you'd push the hand controller left, just like a regular old airplane.
Oh, it really is.
One thing that's different about this vehicle is you notice we've got some what we call cathode ray tube displays. We got 3 of them. You don't see those in conventional airplanes because the need to display a variety of information with limited space isn't quite so critical as here.
Now, the shuttle will be taking scientists and engineers, men and women of all races, into space, just like the astronaut crew on the Starship Enterprise. So that is why I'm speaking to the whole family of humankind, minorities and women alike. If you qualify and would like to be an astronaut, now is the time. This is your NASA, a space agency embarked on a mission to improve the quality of life on planet Earth right now.
January 31st, 1977, the Mojave Desert. Space Shuttle Orbiter 101 is being transported from its assembly facility in Palmdale, California, 35 miles overland to NASA's Dryden Flight Research Center at Edwards Air Force Base. This orbiter, named Enterprise, is the first of a fleet of reusable space transports. Like nothing ever before built, the shuttle orbiter is a hybrid, part spacecraft, part airplane. Upon returning from space, the orbiter, with no air-breathing engines, will be flown to a powerless landing like a glider. Now, performance and reliability must be proven in the approach and landing tests of the orbiter Enterprise. For testing,
The 75-ton spacecraft will be carried atop a 747 jumbo jet to an altitude of about 5 miles, then released by firing a set of explosive bolts. The test will be carried out in 3 stages: the captive inert phase with no orbiter crew aboard, then the captive active and the free flight stages, both with astronaut crews at the orbiter controls. Taxi runs begin the captive inert testing, in which the orbiter stays atop the carrier aircraft and none of the orbiter's systems are turned on. The big 747 is maneuvered along the runway at speeds up to 157 miles an hour to determine steering, braking, and ground handling characteristics while carrying the orbiter. Next, a series of 6 captive inert flights is scheduled, still with the orbiter unmanned and its systems inactive. 747 Captain Fitz Fulton and co-pilot Tom McMurtry will fly the carrier aircraft as chase planes help monitor the operation. Their mission is to obtain information on performance of the mated vehicles. The crew is pleased. Handling is much closer to that of a standard 747 than expected. Subsequent captive inert flights check for stability and control problems and accomplish flutter tests. Flutter is a term for high-frequency oscillation, which can build up in aircraft parts, causing structural failure. The orbiter's position atop the carrier aircraft changes the normal airflow around the 747 tail, reducing stability and causing tail buffet. For this reason, special fins, resembling outriggers, have been added to the horizontal stabilizer to restore directional stability. A tail cone fitted to the orbiter and covering its 3 main engines allows it to be carried higher while reducing 747 tail buffeting. After separation, since the tail cone also reduces air drag on the orbiter, it will be able to descend more slowly, allowing more time for testing in flight. A tail cone will also be used to reduce tail buffet on ferry flights when the 747 transports orbiters from California to the launch facility in Florida. But for space missions, the orbiter's engines will be left exposed and the vehicle will re-enter the atmosphere and land without a tail cone. The captive inert flights continue with technical evaluations. Emergency descent is simulated. Finally, all procedures up to the point of actual release of the orbiter are carried out. The testing goes so well that flight number 6 is not required. The captive active phase can begin with the orbiter crew aboard and the orbiter systems active. Astronaut crews have been training for the approach and landing tests. A shuttle training aircraft, or STA, is constructed by modifying a Gulfstream II airplane to handle like an orbiter. Inside, the left seat and controls are changed. Computer equipment is added. In the STA, a crew practices landings. Spacecraft Commander Fred Hayes and spacecraft pilot Gordon Fullerton. Briefings are held on orbiter systems with another crew, Spacecraft Commander Joe Engel and spacecraft pilot Dick Truly. At the Johnson Space Center in Houston, Texas, a computer-controlled trainer, the Orbiter Aeroflight Simulator, or OAS, is used to practice landings. Orbiter crews operate the controls, causing a special television camera to scan a scale model of the dry lake bed on which the orbiter will land at Edwards Air Force Base. The result, a realistic orbiter landing, is seen through the simulator windows.
Gear coming.
The crews are well prepared. Astronauts Hayes and Fullerton will fly the first captive active test, alternating the missions with Engel and Truly. The control room at Dryden Flight Research Center manages operations before the flight and maintains contact with the carrier aircraft. It will also serve as a contingency control room, in case communication should be lost with the control center in Houston. The control center is the Recovery Operations Control Room at Johnson Space Center, the same control room used for recovery operations during the Apollo program. The orbiter's fuel cells are active now, furnishing 15,000 watts of electricity for coolant systems, communication equipment, and flight control systems, including the 5 onboard computers. 4 of these computers are redundant, working together as a set, comparing information when asked to make a decision. If failures occur, normal operation can still continue with as few as 2 of them functioning. Finally, the crew can fly the orbiter using the 5th computer only if the redundant set fails. Other power is furnished by special hydraulic turbines called auxiliary power units, or APUs. They supply energy for mechanical functions, such as moving the flight control surfaces. It is during these captive active flights that problems occur with the power units. A sensor shows excessive temperature in the APU system, but a later check reveals that it was accidentally triggered by a loose wire. The wire is replaced. Another power unit problem surfaces. A seal in a bellows unit is leaking, allowing APU fuel to drain overboard. The bellows, already being redesigned, is replaced by a modified unit, and the system is safe. 3 captive active flights are made so that problems like these can be discovered and corrected. The last captive active flight includes a full rehearsal for the separation maneuver. The 747 crew pushes over and accelerates the mated pair to 310 miles an hour. They are descending at 3,000 feet per minute. The orbiter's elevons and ailerons are positioned to provide the correct angle and lift for the actual release, the next phase of the approach and landing tests. Astronauts Fred Hayes and Gordon Fullerton will man the Enterprise for its first free flight. Of the scheduled series of free flights, 2 are considered the most critical. This flight and a later one for which the turbulence-reducing tail cone will be removed. Free Flight 1 will test the separation, the handling qualities of the orbiter, and certain systems will be evaluated, including braking and steering during rollout. Now the 747 is near the altitude required for the pushover maneuver. The crew of the orbiter Enterprise is completing its pre-flight checklist. Due to buffeting, the ship vibrates, causing the astronauts' voices to shake.
We're in 202. CSS. CSS, they're steady. Surface is steady. Okay, I'm all set to push over. Get the cameras at the wideband and then the arm at 240. Okay, Enterprise is set. Thanks for the left bits.
905 and Enterprise Houston is go for pushover.
905. Copy the launch heading.
Houston copies.
2, 1, pushover.
Houston copies pushover.
The carrier aircraft has pushed over and acceleration begins. The orbiter pilot will arm a series of explosive bolts, and when separation speed is reached, the commander will fire the bolts, releasing the orbiter. An orbiter pitch-up maneuver will provide vertical separation, and the 747 will turn left, while the orbiter turns right for horizontal separation. Then the crew of the Enterprise will be on their own, flying to an unpowered landing on the dry lake bed.
220, 235, 240, mark. Arm, no lights, 2 lights. Okay, we are armed, 2 lights, and orbiters go. 250.
Houston is go for SEP. Have a great flight.
And we're standby for the bang, Gordo. Power. Stand by. Wasn't too bad now.
At separation, computer number 2 stops processing data. The other general processing computers, or GPCs, in the redundant system voted off the line. The crew informs the control center, executes the planned computer malfunction procedures, and Free Flight 1 continues.
Okay, pitch up. We're up. Got a mass alarm. Computer light, it's number 2. Okay, we got a GPC light, loss of sync on 2, pushing over. And a big X on computer number 2.
Roger, we understand.
Roger. Yeah, yes, yeah.
Okay, she's flying good. 250, starting flare.
Okay, your AA breakers are coming out. And we're going to get a message.
Yeah, that's a definite lurch.
Sideways lurch, just like they said. Okay,
Okay, 11 Alpha, pushing over. Okay, I got you 195 and 20,000. You got it, Gordo.
I got the airplane.
Okay, straight.
Okay.
Enterprise, you're cleared to start the turn.
Okay, Gordo's in the turn. It is really tight, Bo. In fact, I think it's a little better than the old STA field.
Yeah, the lurch is there, just like everybody said. Okay. Altitude's on, and I'm about 14 lower than you are in speed and right on altitude.
The orbiter is not controlled like a standard airplane. The onboard computer system, using information provided by flight sensing devices, makes constant adjustments to the control surfaces so that a stable attitude is maintained. When the pilot moves the control stick, the signal goes first to the computer system. The computers instantly adjust the control surfaces so that while the pilot's command is obeyed, stable flight is maintained. If the weather is bad and visibility poor, the orbiter can be flown in an auto-land mode. In auto-land, the orbiter is brought to a landing by the computer, which determines its location, direction, and speed through its inertial guidance system, its microwave landing system, and other data sources.
Got a steady auto land, 900. Armed.
Okay, we are armed and flaring.
Standing by the gear.
200 feet, 290. Okay, the gear is coming down at 270. Coming down.
Mark.
Gear coming. Doors open and they're all down. Some are down. What's down here? 50
Okay,
feet.
3 downs. Gear's down.
40
240. 230.
20.
220, lots of speed.
10.
Beautiful.
Holding 10.
210.
220 at about 5 feet.
210.
4 feet. Getting some dust.
200.
3 feet. 2 feet.
195.
Just overlap about 2 feet.
185.
You're on. You're on.
Okay, speed brakes. Speed brakes are coming.
About 10 feet.
Speed brakes are halfway out.
We'll see you, babe.
Okay, I got 130 knots.
Okay, that's great.
120.
Little rudder.
115. Okay, 80. Okay, 60 knots. Try the nose wheel.
Okay, that was too good a glider.
Free flight time, 5 minutes and 22 seconds. Roll out with moderate braking, a little over 2 miles.
It's a lot better than the OAS. Look at that.
Free flights 2 and 3 have furnished additional engineering data. Required adjustments have been made to Orbiter 101 systems. Now, astronauts Joe Engel and Dick Truly will make free flight number 4, the first flight with the tail cone off. When an orbiter returns from space, it will not carry a tail cone. This will cause increased turbulence behind the craft and will create more air drag. During this critical flight with the tail cone off, the tail section of the 747 will receive even greater punishment from the turbulence. But if all goes well, the 150,000-pound Enterprise will be released and will descend 20,000 feet in 2.5 minutes. First, the mated vehicles are checked in flight with the orbiter's tail cone off. A data run is made to monitor performance at separation speed. Then the 747 begins its climb for pushover and actual separation.
Smoothly. Enterprise has 2 lights. We're go for SEP.
Roger, Enterprise. Houston is go for SEP. Go for SEP.
Okay, Dick, let's do it pretty. 210 knots. 220 knots. 230 knots. Stand by for launch ready, Joe. Okay. SEP. Okay. Coming up. Body flap set. Good. Okay, pushing over. Okay. Okay, Joe, we're configured. Beautiful. 180 knots.
Free Flight 4 is going well.
Got it.
Instrumentation and power systems are performing normally. Carrier aircraft buffeting was within the established limits before separation. And during free flight, The orbiter's handling qualities are not noticeably different than they were with the tail cone on.
285 knots, you're looking good. 290 knots, 4,000 feet. 3,000 feet, 290. You're a little fast, Joe.
Leave them out.
Pre-flare.
You're on the glide slope. We see you on the glide slope.
Want the speed brakes coming in?
Negative. Leave them. Okay, now start them in.
Okay, they're coming in. Speed brakes closing.
Orbiter gear.
Okay.
Get the gear.
Gear's coming. Okay, 200 feet, Joe, 260 knots.
Down.
Good. 250 knots. 240 knots. 230 knots.
10 feet.
220 knots.
5 feet. 4
10
feet.
knots. 200 knots. 190 knots.
Down.
Speed brakes are tracking.
Nose is coming down. 2 feet. 1 foot. Down.
Brakes.
Back up. Nose wheel steering on. Off. Differential braking. Your brakes, Dick.
Okay, I've got the brakes.
Push them hard.
Okay.
Okay.
Okay, let me get a little slower here, Joe. Okay, I'm coming off the brakes.
Okay.
I'm on the right brake.
Okay, I'm coming in slow. Come on, brake. I'm holding what I got.
Okay. Okay, Houston, we're stopped. Mark.
Roger, got it.
Good for here.
Thank you, Richard. That was a super one.
Pre-flight time, 2 minutes and 35 seconds. Rollout with hard braking, 5,275 feet. The orbiter flies well with the tail cone off. On this flight, free flight 5, the orbiter will land on a paved runway. The performance of the landing gear and its connected airframe systems must be verified on this type of surface. Also, the orbiter's approach, landing, and rollout will be tested on the paved strip with a simulated 10,000-foot length. The Kennedy Space Center runway, where the orbiter will normally land as it returns from space, is 15,000 feet, and the additional 5,000 feet will mean a greater margin of safety. Free Flight 5 goes well until just before touchdown. Then a pilot-induced movement takes the vehicle close to the ground. It rises. At 187 knots, it touches down, but skips off the ground and settles 1,900 feet later to a second touchdown. The total runway rollout distance from the first touchdown point is 7,930 feet, well under the 10,000-foot mark. With Free Flight 5, the approach and landing tests are concluded. All of the assigned program requirements have been satisfactorily completed. Now Orbiter 101 will go to Marshall Space Flight Center in Alabama for a series of ground vibration tests. In 1979, the 747 will carry Orbiter 102, sister ship of the Enterprise, to Kennedy Space Center in Florida, where it will be the first vehicle to be used in the orbital flight tests. Each shuttle orbiter is designed to be used at least 100 times. The Space Shuttle fleet will handle a variety of missions: placing, servicing, or recovering satellites in orbit, delivering deep space probes for on-orbit launch, carrying space laboratories. NASA's Space Transportation System will replace nearly all expendable launch vehicles for both civilian and military space missions. With the shuttle orbiters, we're entering a new era in space.